Okay. So I think this is now the 9th lecture of linear programming. And so what we're going to do today is we're going to talk about different types of solutions. We're going to talk about feasible solutions and optimal solutions, which we've seen before. But we're also going to talk about basic feasible and basic optimal solutions. So we've read these words a couple of times. The main purpose of these words is to highlight the fact that these are a really good subset of the solutions to look at. And the hope is that by understanding what's going on here, we can solve the problem in general with a lot more ease. Unfortunately, this means I'm going to have to require some linear algebra. I know it's been a while since some people have done linear algebra, so I think it's not a bad idea to just quickly review. So I'm hoping that this is a review. There are stories of a linear algebra class taught here years ago where they did not mention the word eigenvalues. So review of linear algebra. So the main thing we need is a basis. So V1, Vn is a basis of some space V if any V in V is a unique linear combination of the VI's. So we can write V as A1 V1 plus AN Vn, and if alpha 1 V1 plus alpha n Vn equals the 0 vector, then all the alphas are 0. Right. I'm assuming here that my space is finite dimensional. For most of what we're doing, things will be finite dimensional. It may be a huge finite dimensional, but it will be finite dimensional. And depending on what problem you're doing, different bases are more natural than others. So if you're in Manhattan, Manhattan has a very obvious north, south, east, west basis. Okay? If we were doing ellipses, we had talked, I think, in the past about having an ellipse oriented like this. And in this case, it would be much better to use these as my basis directions. You might have seen the phrase principal axis theorem. How many of you have heard that phrase? All right. They sometimes use that in linear algebra, that if you have a real symmetric matrix, there's a really good basis of eigenvectors. And that makes it a lot easier to deal with what's going on. OK. So I'm not going to bother going through examples of how you write things down in bases and whatnot. I'm going to assume that this is all clear. But if there are any questions, of course, feel free to ask me. All right, so what we want to do is we want to talk about a basic feasible solution. So consider the canonical problem. So by now we have constraints. Ax equals b, x greater than or equal to 0, and we want to minimize, so this is our objective function, C transpose x. Okay? So we say a feasible solution is basic if the corresponding column entries of A to the non-zero entries of X are linearly independent. Okay, so what would that mean? So for example, if x equals 0, 1, 3, 0, 0, 7, 1, then we would want the columns A2, A3, A4, A5, A6, A7 are linearly independent. And typically what we would do in a situation like this is we would write our matrix A as A1, A2, A7, I guess in this case, where these are just going to be the columns. Okay. So the definition is pretty straightforward. It says here, if you take a feasible solution, all you need to do is look at the corresponding entries, the corresponding columns. Why? So this goes back to thinking about what matrix multiplication is. There's a lot of different ways to view matrices. You can view a matrix as a transformation written down on a given basis. What does it mean to solve AX equals B? Let's say that there's a solution to AX equals B. This means B is in the column space of A. Is it sounding vaguely familiar? And you get that highfalutin fundamental theorem of linear algebra, which I believe is overrated on all the different spaces. But this implies B is in the column space of A, i.e., B equals x1 times the first column. I think I'm doing it as, I want to make sure it's m rows and n columns, yes. And xn an. So this is another way to view matrix multiplication, or what happens when you have a matrix acting on a vector. You're taking a linear combination of the columns. And for AX equals B to be solvable, then B must be in the column space of A. It must be some linear combination of the columns. The whole idea of the basic solution is the following. If a corresponding x is 0, does that column matter in solving for AX equals B? No. If any term here is being multiplied by 0, I can just drop it. So this is the same if I1, I2, dot, 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 IK are the non-zero places, then AX is the same as XI1, AI1 plus XIK, AIK. Because any column that's multiplied by 0 does not come into play here. Okay? So how many of you ever read Choose Your Own Adventure stories as a kid? All right, so we have a Choose Your Own Adventure here. We can prove that either, first, if you have a feasible solution, you have a basic feasible solution, or we could prove first that there are only finitely many basic feasible solutions. First loud voice wins. Probably even first medium voice wins. Any preference? Would you rather know that if you have a feasible solution, there's a basic feasible solution, or would you rather know that there's only finitely many of them? Which do you think is the more fundamental?
If you have a feasible, you have a basic.
I think that's the more fundamental one. The second claim is why it's useful. The fact that there's only finitely many basic feasible solutions gives you a sense of why we would care about a result like this. But the fact that if you have a feasible solution, you have a basic feasible solution, then that tells you that this is a potentially good thing to study. All right, so let's do that one first. I feel like I'm doing the moonwalk. OK. So we don't need linear algebra anymore. So theorem. If the canonical linear programming problem has a feasible solution, then it has a basic feasible. Right now, we're not saying we know how to find the basic feasible, and we're not saying how many there are, just that it exists. Frequently, for many problems, it is trivial to find a feasible solution. Okay? Imagine you own a movie theater. I'm not even going to bother telling you the constraints. Can you give me a feasible solution to the constraints if you own a movie theater?
Show one movie.
Nope. Oh, I mean, that would probably work, but something even easier than show one movie. Show no movies, right? So whatever constraints I have, I don't want too many people coming in or coming out at the same time. I don't want one movie on multiple screens at this. Show nothing. That will satisfy all your constraints. You'll go bankrupt, but it will satisfy all your constraints. Somebody give me a feasible solution for an airline. No flights. Okay? So in a lot of situations like that, you'll be fine. Now the diet problem, if you say eat no food, that's not going to work. Okay? But there are a huge class of problems where it is trivial to find a feasible solution. And then what this tells you is that you can immediately pass from that to a basic feasible. Okay, proof. It's the method of descent. This is why it's nice to be a number theorist. All right. We talked about the method of descent when we were looking at the square root of 2 being irrational. You can use the method of descent to look at Fermat's last theorem and related questions like that. Of curiosity, how many of you have seen the method of descent in another class? Okay. Not too many. It's an extremely powerful technique. The main idea is you start with a solution with a certain minimality property or a certain maximality property, some kind of extremum. Usually we like to do minimum. And you say, let's assume a solution exists, and let's assume it has the smallest possible value of this quantity we care about. Then we show, given such a solution, we can construct a new one that's even smaller. How can we construct something that was smaller if the previous one had the minimum value? The only way we can do that is if there was no one that had a minimum value. And that assumption must be wrong. So that's how it works. We assume a solution exists with a certain minimum property. So start with a feasible solution with a minimum for some property. And then we'll show if it's not basic, then must have another feasible with a smaller value. So again, what I really want you to get out of this is the method of proof, how you would attack a problem like that. Most of you are not going to become professional linear programmers later in life, okay? But if you are, there's a lot of money that can be made like that, so please stay in touch. But the idea of how to approach these problems, that's going to serve you well. And so I'm trying to deliberately hide a couple of things. So we want to start off with something that with the minimum property, and then the whole idea is we want to show that that thing is basic. That's our candidate. Whatever the minimum value is, that's our candidate. So assume it's not basic. Then somehow we can use the fact that it's not basic to construct a new feasible solution with a smaller value. Contradiction, therefore it must have been basic. Unfortunately, for this to work, we have to come up with what that property should be. So any thoughts on what the property should be?
You have to know that there is a minimum for that property, right? Because otherwise you could just assume that there exists
Yes.
the wrong function.
Right. So for instance, we do need to know that there is a minimum. Now, if you go back to the square root of 2 example, and we're writing square root of 2 as a ratio of 2 numbers, since the 2 numbers have to be positive integers, we know that there's a certain minimum. And we know that it can't go all the way down to infinity. But you're absolutely correct that for some things, depending on what we look at, you could actually have a chain going down. So we need a property that clearly has a minimum value. And in fact, it gives you a clue. So positive integers, subsets of positive integers have a minimum property. Subsets of the reals do not necessarily have a minimum. So this is giving us a clue that maybe the minimum property we want should be related to some kind of integer count. Any thoughts as to what that should be? So I need to come up with some property, and somehow if it's not basic, so that means that that the corresponding columns are not linearly independent, I can somehow get a solution that has a smaller value of this property. Any thoughts on what that property should be?
I want to say like C transpose X. Because
So C transpose X, it's a good thing to try, but it can't be right, because C transpose X is the objective function. And right now we're just talking about the feasible solution. So the objective function can't play any role. It's good to try to see what...
What about X transpose X?
So one thing is potentially the norm of the vector. That's not a bad thing to try and say that...
Because can we show that we can, if it's not basic, then we can write some column as a linear combination of the others, and then remove that, and then we now decreased our...
Good. We haven't necessarily decreased the norm, but we've decreased the number of non-zero entries. So you're basically right. It's not X transpose X that we want to look at. We want to look at how many non-zero entries does our feasible solution.
Minimum number of non-zero entries.
Right.
And then show that we can reduce that.
Exactly. And if you look at the definition of basic feasible, which is about to go the way of the dodo, it talks about the non-zero entries, right? So in terms of what we can use for our property, that seems to be a real clue that if this is going to be a useful definition, somehow we should be working in the non-zero entries. Okay. And then again, right now what we're going to do is we're going to assume that we have a minimal solution, not necessarily the minimal solution. Okay. It's possible that there could be many solutions that have the fewest number of non-zero entries. So assume X is feasible, not basic, and has fewest number of non-zero entries. So there could be lots of different solutions that have the same minimal number of non-zero entries. So we can't say we take the one. If we wanted to, we could probably put some kind of ordering on the solutions and say if there's many of them, choose whichever one has the smallest value of x1. Well, then it's potentially dangerous because maybe we have infinitely many of them and maybe there is no minimum. You've got to be very careful to make sure that whatever process you choose, there is a clear minimum. And this will definitely be a representative. So what does this mean? This means we can write B as x I1 AI1 plus x I k AK, the x I L do not equal 0. All right, now it's worthwhile to just stop and pause for a moment. The notation is getting a little bit painful with subscripts on subscripts, correct? We have two options. Option one is to say, well, you know, this is mathematics. We have subscripts on subscripts, and let's march on. Option two is to say, why don't we just reorder our variables and assume it's the first k entries that are not 0?
Just to back up.
Yes.
What is xi1? Because isn't x just a vector?
X is a vector. This is the I1th entry of x. So if I1 equals 5, it's the 5th entry of x.
Oh, okay. So it's not like xi1. It's
No,
xi1.
it's right, because I don't know where the first non-zero entry is. It's somewhere. I don't know where the second one is. It's somewhere. Right? So I can't just write x1 because x1 would be the first coordinate. So we have two options. One is to just keep subscripts on subscripts, and then we'll occasionally make mistakes and forget to put the I above the k. Or we can just say, look, why not just reorder the variables and have, you know, without loss of generality, 1, 2, 3, 4, 5, k, those are the non-zero components. All that is just shuffling the columns, right? How many people are in favor of shuffling columns? Yeah. So it's the most powerful. So without loss of generality, B is equal to x1 A1 plus xk AK xi greater than 0. Now this is my favorite logarithm. This just makes it a lot cleaner. Okay?
So should that be not equal 0?
Well, we know the x's are greater than or equal to 0. So if it's not 0, it has to be positive.
Right. So I mean, okay.
So yeah, I mean above here, yes. Yes. What I wrote was correct, but not as correct as possible. I could have been more correct and said greater than 0 there as well. Corrected the mistake later. Okay. Since it's not basic, there exists alpha 1, alpha k, such that alpha 1, a1 plus alpha k, ak equals 0. Right? So when in doubt, go back to the definitions. If you're told something is not basic, what does that mean? It means that there's a linear combination which equals 0, and not all alpha I are 0. So at least one of the alphas must be non-zero. Which alpha I is non-zero? Right, why? Good. Without loss of generality, alpha 1 does not equal 0. Is it possible that alpha 1 is the only one that's not 0? So here's a question. Is it possible that alpha 1 is the only one that's not 0? I'm sorry? There is one way alpha 1 could equal 0 and this combination could equal 0. What if all the other column A's are all zeros? Then this would be really stupid. It would be a really stupid problem, right? We don't want columns that are zeros. What would it mean for a column to be all zeros? Might as well not exist, because then the corresponding variable has nothing to do with it. When you're trying to calculate how many runs the Red Sox will score this year, it really does. I mean, we were talking about my baseball managerial prowess earlier today. I do not think that inputs at all into calculating how well the Red Sox will do this year. It is completely immaterial how well I coach in Williamstown, sadly, for how well the Red Sox do. I have no impact. So if we have a column that's all zeros, why are we including it? So when we look at a canonical linear programming problem, we might as well assume every column has at least one non-zero entry. Okay? So you've got to be a little bit careful when you're doing things. We will talk a little bit more about this when we start doing the simplex method. But I'll just leave it like that. But you do have to occasionally be careful about that. And so when we state what the canonical linear programming problem is, we probably want to also add there is no column that's all zeros, because really, why would we do that? OK. So without loss of generality, alpha 1 is not equal to 0. So probably there's got to be another alpha that's non-zero to balance that. But we don't really need that. So what we're going to do is we're going to consider a new solution, xt, which will be x minus t times the vector alpha 1, alpha k. And if we apply the matrix A to this, A of x of t is equal to A of x minus t, oh, I guess this should be a transpose because I'm supposed to be writing this as a column vector. It should be t A applied to the vector alpha 1, alpha k. And what is A applied to the vector alpha 1 through alpha k? What will that be? 0. We've just chosen the alphas so that when you take that linear combination of the columns, you get 0. So this is just AX. But we know what AX is. That's just B. You've got to be a little bit careful here. Technically, what I should be writing is something slightly different. There's a small mistake here. What is the small mistake? Yes?
You need extra zeros.
I need extra zeros. This is one of the reasons why I always put arrows on my vectors, so I remind myself that they're vectors. You've got to always ask yourself, what is the dimension of the object? Is it m elements? Is it k elements? A requires a vector with n components. This only has k components. If k is less than n, it's not enough components to do the multiplication. Now, it's trivial. I just pad my stuff. Sometimes what you might do is you could put a subscript, maybe a k cross k over here, to just say we're just restricting A to those k columns. Or you can just pad things. So the best thing is probably to just pad. So we'll put on a bunch of zeros down here, and we'll put in a bunch of zeros over here. Okay, so let's recap what we did. We started off with a basic solution that had the fewest number of non-zero components. And now we're subtracting off a very special vector. And no matter what value we take, it still solves the constraints. Well, we only checked half the constraints. xt solves ax equals b. What about xt greater than or equal to 0? Are the components greater than or equal to 0? So we're getting x1 minus t alpha 1 dot 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 xk minus t alpha k, and then a bunch of zeros. Okay, this part is no problem. Those parts are clearly greater than or equal to 0. What about these values? Are these values always going to be greater than or equal to 0?
Can we choose t so they are?
So we can choose t so that they are. Because all of the x's are positive, yes?
I was going to ask why we can do that. Yeah.
I'm sorry?
I was going to ask why we can do that.
So because all the x's are positive, if t is sufficiently small, each component will be positive. So I think it's like choose t to be less than the minimum of like xi divided by alpha I in absolute value over I such that alpha I does not equal 0. Although if alpha I equals 0, then it doesn't matter what you take over there. If we choose t sufficiently small, none of these will be enough to subtract off to make something negative. So you can quantify exactly what it is as to how far you can go. It doesn't really matter how far you can go. All that matters is that there's some choice. We're not trying to find something. We're just trying to prove the existence. So if this is 15 and this is 3, we could take t up to 5. Yes?
If we choose t equals the min, can we just be finished?
So that's where things come. Now we choose t to be the minimum. And we choose t to be such that the first one, and we have to be careful about the sign, but we now choose t so that one component vanishes, or at least one component vanishes. So when t is sufficiently small, all are non-zero. Eventually, as t is getting positive or negative, we will reach the point where one component becomes 0. Maybe several components become 0, but we will reach the point where at least one becomes 0. So as the absolute value of t grows, we reach a point where at least one component is 0, or I guess one new component is 0, and the rest are positive. And that's a contradiction. We're done. We assumed that we had a feasible solution with a minimal number of non-zero components. We just found a feasible solution with fewer non-zero components. Contradiction. Well, what was our assumption? Our assumption was more than just x was a feasible solution with a minimum number of 0 components. It was a feasible solution with the fewest number of non-zero components, and it was not basic. So if there is a feasible solution, then there is a feasible solution which is basic. Okay? Any questions about this? Yes?
Did we just define x of t like that, or was there a specific reason why we subtracted the alpha?
There was a specific reason we subtracted the alpha. So we decided to define x of t this way. So we started off with our solution, and then we subtracted off basically the vector coming from the alphas. And the reason is we know that if we look at alpha 1a1 plus dot 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 alpha k a k, that linear combination is 0. So it's not going to affect whether or not, we knew x solved the constraints ax equals b, xt also solves axt equals b. So this gives us a new feasible solution. We had to check and make sure that it was feasible. It's not necessarily going to be feasible for all values of t. In fact, since one of the alphas is non-zero, if t either becomes very positive or very negative, one component will become negative. So there will definitely be choices of t such that xt is not a feasible solution. But the idea is that for small values of t, this is still a feasible solution. Let t grow either in positive or negative space, and eventually at least one component will vanish. And by some nice results in real analysis, we have the, oh god, it's been so long, the intermediate value theorem, right? You can't go from positive to negative without going through 0. So really the intermediate value theorem is lurking in the background here. So as we go from positive to negative, at one point we must be 0. Okay. Any questions about this? Essentially the same argument proves that if there's an optimal solution, then there's a basic optimal solution. I may not go through that proof in class because it's essentially the same as this. Not surprisingly, there you use the objective function. Right? Yes?
Could you state how the contradiction solves the problem?
Sure. So we're assuming that in our problem we have a feasible solution. And we're showing that if there's a feasible solution, there must be a basic solution. There may not be a feasible solution. There are some problems that do not have feasible solutions. But let's assume that there's a feasible solution. Then we must have a basic feasible solution. So let's assume that there's no basic feasible solution. All right, what would it mean? Well, if there's no basic feasible solution, let's look at all feasible solutions, and let's look at the one that has the fewest number of non-zero entries. Since we only have n components, we have at most n entries that are non-zero, and at least 0. Okay. The solution of all zeros is not that interesting, so we'll assume we don't have that case. So look at all the feasible solutions. Look at all the ones that have exactly n non-zero entries, exactly n minus 1 non-zero entries, exactly n minus 2. There's got to be one integer value such that there's nothing smaller than that. So maybe the smallest that works is 5. We have feasible solutions with 5 non-zero entries, but we have no feasible solutions with just 4 or fewer non-zero entries. So now we look at all the feasible solutions with 5 non-zero entries, and we choose one of them. And it's very important that we don't have to choose a specific one, just choose any one of them. Now that we have that one, since we're assuming it's not basic, then that means the corresponding columns are not linearly independent. So what that's telling us is there's a way to pass from this feasible solution to a different feasible solution. And that new feasible solution is going to have fewer non-zero entries. And that contradicts the fact that this had the fewest number of non-zero entries among our feasible solutions. So our assumption that there was no basic solutions must be wrong. And so now we know that there has to be at least one basic feasible solution. Okay? The proof is essentially identical for optimal. Okay, so what I'm going to do is I will just state the result, and I will not go through the proof. If the canonical linear problem has a feasible, has a optimal solution, then it has a basic optimal. So what this is telling us is rather than looking at the whole space of solutions, it suffices to study this subset of solutions. The question is whether or not this is good. Are these solutions easy to access? Are they easy to work with? If they're not, this is not a good deal. How many of them are there? If there are too many of them, bless you, it's not going to be worthwhile to study them. Okay? So this tells you that it may be a good idea. Now I'm going to show you it is probably a good idea. So new theorem. There are only finitely many basic feasible solutions. Now, an optimal solution, is an optimal solution feasible? what do you think you can get immediately as a corollary? So let's say we know that there are only finitely many basic feasible solutions. What should we be able to get as a corollary?
There are only finitely many optimal.
Yeah, well, not optimal. Close.
Basic optimal.
Basic optimal, right? So corollary, only finitely many basic optimal. Has anybody here done algebraic number theory? All right. I needed to prove that the irrationality exponent in a paper I was looking at was finite. And I think I was able to show, this is an aside, I got a bound that it was less than or equal to, I may be off by a little bit, 10 to the 602, which is finite. And so I was done. Now, this is not a good bound. Okay, it's significantly less than this. 4 might suffice, I'm not sure. But something much, much less than 10 to the 602 works. But I just needed to prove that it was finite for the argument to run through. And so I did the crudest argument possible, to just quote big guns in the literature. The fact that there's only finitely many solutions, this is great. Unfortunately, if the finite number is too large, it's going to be impractical. So right now, this is giving us cause to hope, but we're not there yet. We have to find an efficient way to search the space of feasible solutions. But at least there's only finitely many things to search. Okay. So we want to prove the theorem now, that there are only finitely many basic feasible. So proof only finitely many basic feasible. So we have A is m by n. X is, how many components does the vector x have? It has n components. Or is it m components? M components. And then B. I'm sorry, yes, it's n components, yes, thank you. It's n components. And then B has m components. Now we want to look at basic feasible solutions. So what we can do is, if we can just show for each k, there are only finitely many basic feasible solutions with k non-zero entries, we're done. Show for each k only finitely many basic feasible with exactly k non-zero, and then just sum. Right? What's the largest value of k we need to look at? Why n? There's a really nice justification why n suffices.
What is K?
Well, we're going to show for each k that there are only finitely many basic feasible solutions with exactly k non-zero entries.
Right, no, but K is K is the number of non-zero entries, right?
Right.
So you therefore can't have more than
Can't have.
n non-zero entries.
Right.
N length vector.
Right. So clearly k is at most n. Right. Maybe we could do something better than n, but clearly it can't be larger than n. Okay? So now what we want to do is just show that if we have k, any finite k, there's only finitely many basic feasible solutions. So now, how many candidate columns are there for each k? So let's say we have a specific value of k. Maybe k is 5. Then that means we want to look at 5 columns of A. So given k, we have n choose k ways to look at k entries of x or k columns of A. So if k is 5, there are n choose 5 ways to choose 5 columns of A. I can't choose the same column twice. So all we have to do now is show for each one of these, there's only finitely many. Okay? So let's say you have AI1, AI2, dot, 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 AIK, XI1, XI2, XIK equals B. How many solutions can we have? So this is the main part. We want to show that there's only finitely many solutions here. Right? Because if we can show there's only finitely many solutions here, there are only finitely many matrices like this, or choices of k columns like this that we need to look at. And there's only finitely many choices of k. Yes?
So we at this point have linear independence, right?
So good. We know these columns are linearly independent. So if we call this matrix maybe M, I'll maybe do M with a k in parentheses, X with a k in parentheses equals B. And we know M has linearly independent columns. So the question is it possible that we could have infinitely many solutions to this? Remember, in matrix equations, you either have 0, 1, or infinitely many solutions. All we have to do is show that there's not infinitely many solutions to this. So what would it mean to be infinitely many solutions? There would have to be a null space. Right? We would have to be able to add some vector which is sent to 0 by this matrix M. This matrix has no null space. So there's at most one solution. There's a solution if B is a linear combination of the columns, otherwise no. So solution only if B is a linear combination of columns, at most one solution, as null space is just equal to the 0 vector. Another way of looking at this, let me see if I can do this correctly, is I multiply both sides by the transpose of MK. And this matrix turns out to be invertible. This is a k by k matrix, and it's invertible. So as a nice exercise, revisit your linear algebra, prove this k by k matrix is invertible. Well, if this matrix is invertible, let's see, am I able to then do this? So check, I think it's invertible. So if it's invertible, then this would be true. You've got to check. I'm not sure if this is invertible. I'll let you check that. This part is definitely correct. Because the only way, because if you had two different solutions, I could subtract. This seems scary. What this is telling us is, oh my God, every choice leads to a solution. Crap, not only is it finite, it's large and finite. Fortunately, there is a condition we have forgotten. What condition have we forgotten? So I'm pretty sure this works. I'm pretty sure this is invertible. And this tells you, oh my God, there's always a solution. No matter which choice of k columns you take, as long as they're independent, there'll be a solution. Something seems wrong. What's the problem? So if we take just one column, do we expect there to be a solution? No. So it's got to be b's in the column space. So we do not expect that there always is going to be a solution. So because we don't expect there always to be a solution,
So maybe k is always between m and n?
so one thing is maybe k is always between m and n if we want this to work. So this part here needs work. There's a good idea here, but you've got to make it work. It's always nice to stop and think what's going on. Check some extreme cases. This is telling me if I just take one column, I can always solve that column. And that would mean B is a multiple of every column. So clearly something is going wrong. And we want this space to be large enough to capture B. So maybe once we are as large as M. So maybe you're OK if k is greater than or equal to m. And in fact, later on, we will only look at b's that are not linear combinations of fewer than m columns. But going back here, this is basically saying we can always solve. So the issue is, are all of these solutions going to be feasible? It's not enough to solve ax equals b. What else do we need? I'm sorry? We need more than just ax equals b. We need one other item. X is greater than 0. And that's what saves the day. Need x greater than or equal to 0. Most of these fail. So we would have been fine even without this observation. It would still have only finitely many solutions. The problem is the number of finitely many solutions would be so large as to be impractical. What goes on here is because the components of x have to be greater than or equal to 0, most of these solutions won't work. But what we've shown is for each value of k, there are n choose k possibilities, and each of those possibilities has at most one basic feasible solution. So the number of basic feasible is less than or equal to the sum of n choose k. K goes from, make it go from 0 to n, and that should be less than or equal to 2 to the n. Okay? So this is enough to prove that there's only finitely many. All right, so this is a good place to stop. I might talk a little bit about some connections with prime numbers just in terms of looking at how efficient these things are. But what we've now shown is there's only finitely many basic feasible and basic optimal, and the goal will be to then use that and